All right, welcome back to the deep dive. Today we're diving into some seriously mind-bending stuff. We're talking about the physics of Gottfried Wilhelm Leibniz. You know, that guy who was right up there with the giants of the scientific revolution, like Galileo, Descartes, Newton, all those big names.
Absolutely. Now, a lot of folks know Leibniz for his big metaphysical theories and his super optimistic view of, well, everything. But his work in physics, really profound. It's often kind of overshadowed.
Totally. He wasn't just sitting back theorizing about the universe. He was right in the thick of it, tackling those same big questions about the physical world as, his more scientific buddies.
Exactly.
So where we're headed with this deep dive is we want to unpack the core of Leibniz's philosophy of physics, his ideas about reality, the nature of matter, how things move, space and time, the whole shebang. And to help us navigate this intellectual jungle, we're relying on the Stanford Encyclopedia of Philosophy's entry on, well, exactly that, Leibniz's philosophy of physics.
It's a pretty dense read, but it gives us a really solid roadmap to understand the intricacies of his thinking.
Right, so we'll trace the evolution of his ideas, see how he butted heads with the prevailing theories of his time, and dig into his own super innovative concepts. Sound like a plan?
Sounds good to me.
Awesome. So first things first, where did Leibniz's fascination with physics even come from? What were the early influences that shaped his thinking about the physical world?
Well, right from the start, Leibniz was immersed in this deeply rich intellectual tradition.
Right.
We're talking about the Aristotelian scholastic thought, the dominant philosophical framework of the time. His dad had a pretty impressive library, and then his university education in Leipzig, Jena, Altdorf, it was all steeped in this tradition. And he also encountered Neoplatonism, which was having, a bit of a Renaissance moment back then.
So he wasn't coming at this with a blank slate.
Not at all. And even though he kind of broke away from the scholastic tradition, its influence stuck with him. It gave him this toolbox of concepts that he could, refine, rework, sometimes completely disagree with, but it was all part of his journey.
Right, like a springboard for his own ideas.
Exactly.
Now, I got to ask about this so-called conversion to mechanism
Yeah.
that happened around 1661. Apparently, it went down to the Rosenthal Grove. Sounds almost mythical, right?
It's a great story. So Leibniz is 15, hanging out in this grove, and he's really wrestling with the idea of substantial forms, a core element of Aristotelianism. And it's like a light bulb goes off, bam, he embraces mechanism.
So what does that actually mean? Embracing mechanism.
Basically, he committed to explaining nature without resorting to these mystical, incorporeal things. Instead, he focused on the fundamentals, magnitude, figure, motion things you could actually measure and quantify.
Ah, so shifting from explanations based on some kind of hidden essence to explanations based on the actual interactions of material stuff, right?
Yeah, exactly. And this commitment to a mechanistic view of nature really pushed him to systematically explore the nature of motion. And that's where his early works come in the Theoria Modus Abstracti, or TMA for short, and the hypothesis Physica Nova, which is also known as Theoria Modus Concreti, both published in 1671.
Okay, two theories of motion, an abstract one and a more concrete one.
Right.
So in the TMA, the abstract theory, he leans heavily on this concept of conatus from Thomas Hobbes, basically, the inherent tendency of a body to move in a specific direction. And the wild thing about this theory is that the size and mass of a body, they play absolutely no role in determining its motion. It's all about the conatus.
So let me get this straight. A tiny little pebble, if it has the right conatus, could smash into a giant boulder and keep on moving at the same speed.
That's exactly the kind of counterintuitive implication that this theory had.
I mean, that just doesn't jive with what we see every day, right? It takes way more effort to move a huge thing compared to something small.
Yeah, and Leibniz was aware of that disconnect. He knew these abstract laws didn't quite match up with the real world.
Okay, so how did he bridge that gap in the hypothesis Physica Nova, his more concrete theory?
So in the HPN, he tries to reconcile his abstract principles with what we actually experience. He introduces the idea of the contingent structure of the world, the specific way things are set up in this particular universe. He proposes that all bodies are elastic. They have this springiness to them. And that's thanks to this pervasive ether. Think of it like a subtle fluid that's everywhere.
Got it.
And he also says that all bodies are made up of these discrete particles. Now, mass still isn't a fundamental concept for him at this point, but he cleverly argues that bigger bodies seem more resistant to motion because they have more of these particles.
Right, so it's like a numbers game.
Right.
If a small thing hits a big thing, its motion gets kind of spread out among all those particles in the bigger object. It's not just about the conatus anymore.
Exactly. And that's how he tries to make his abstract mechanical principles more in line with our everyday experience.
Makes sense. Now, the source material highlights these really important years in Paris, from 1672 to 1676. What was it about this time that was so crucial for Leibniz's intellectual journey?
This period was huge for him. He was in Paris for a diplomatic mission, but intellectually, it was a total game changer. He dove deep into the world of math, really advanced stuff for the time.
Okay.
He really dug into Cartesian physics, got super into it, and most importantly, he got to hang out with some of the leading scientific minds of the day, folks like Christian Huygens, who actually tutored him in math and physics. He even got access to some of Descartes' unpublished notes, which is pretty cool.
Wow, so he's getting this like insider's view into Descartes' thought process.
Yeah, and that's when he starts developing his own critiques of Cartesian physics. By 1676, he was convinced he'd found a major flaw in one of Descartes' key ideas, the law of conservation of quantity of motion.
Okay, so that leads us to the brief demonstration and the whole vis vivas controversy, right? A pretty big deal in the history of physics.
Absolutely. When Leibniz published his brief demonstration of a notable error of Descartes and others concerning a natural law in 1686, it set off this huge debate. His main argument was that Descartes' idea of conserving quantity of motion, mass times velocity, it went against a more fundamental principle, the equality of cause and effect.
Interesting.
And for Leibniz, this wasn't just a minor problem with Descartes' theory. It forced him to rethink his own earlier ideas about motion that he laid out in the TMA and HPN.
So his critique of Descartes actually boomeranged back on him a bit.
Yeah, exactly. He realized that his earlier work might have had some of the same issues violating that equality principle. Like in the TMA, a tiny body moving a massive one at the same speed. That seemed even more out of whack with cause and effect than anything Descartes proposed. And the HPN had this idea that the total conatus in the universe would decrease over time. That also didn't sit right with the equality principle.
Okay, so this critique was a turning point. It pushed him to move beyond those early theories and develop his more mature physics, right?
Exactly. He basically doubled down on the principle of cause and effect equality. That became like his guiding principle for understanding physics.
Right.
And he found this new appreciation for Huygens' conservation principle. He'd learned about it earlier, but now it really clicked. He realized that if you think of force not as the Cartesian quantity of motion, but as vis viva living force, which is mass times velocity squared, then those problems with the equality principle kind of vanish.
Okay, so vis viva becomes central to his later work.
Yeah, and that leads to works like the Dynamica de Potentia, the Essay of Dynamics, the Specimen Dynamicum, all these later writings where vis viva is the key concept.
It's fascinating how his critique of someone else's ideas actually ended up propelling his own theories forward. Now, before we move on to his ideas about matter, I got to ask about his famous correspondence with Samuel Clarke. What was the deal with that?
The Leibniz-Clarke letters, those were a big deal. They started in 1715 and went on until Leibniz's death the following year. It was basically sparked by Leibniz's concerns about the growing influence of Newtonian physics over in England. He worried that its emphasis on concepts like, absolute space and absolute time, it could lead to a decline in religious belief. He also might have been a little peeved about that whole calculus priority dispute.
Oh, right, the who invented calculus first controversy.
Anyway, Clarke, he's kind of acting as Newton's spokesperson here.
Yeah.
He fires back at Leibniz's criticisms, and they go back and forth in these 5 letters. They cover a ton of ground, but the biggest clash was over the nature of space and time.
Okay, yeah, we hear about that a lot with Leibniz, this idea of space and time as relational, not absolute.
Exactly. Leibniz argues that space and time are like systems of relations between things, not these independent, absolute realities that Newton believed in. Clarke, sticking to Newton's guns, defended the idea of absolute space and time. It was a pretty fundamental disagreement.
Yeah, totally different ways of looking at the fabric of reality.
Yeah.
Okay, let's shift gears now and talk about Leibniz's views on the nature of matter. I know he was a big critic of atomism, the idea that everything is made of these tiny, indivisible atoms.
Yeah, he was. It's interesting because early on, he actually kind of liked the atomist picture, simple, indivisible particles bouncing around in empty space. It had a certain appeal.
Right, it seems pretty intuitive. So what changed his mind? What arguments did he use to dismantle this whole atomist idea?
Well, a lot of his arguments were tied to his own core philosophical principles that he developed over time. One of his biggest ones was based on this idea called the principle of continuity, basically. Nature makes no leaps. It's this idea that things in nature change smoothly, not in sudden jumps.
Okay.
So Leibniz argues that if atoms were totally hard and inflexible, like the atomist said, then when they collided, their speed and direction would change instantly.
Like a sudden stop or a sharp turn?
Yeah, exactly. But Leibniz thought that true continuity, that smooth change, it requires some degree of elasticity, of give. And for something to be elastic, it has to have parts that can move relative to each other so it can bend a little, then spring back.
Ah, so it can deform and rebound without just instantly changing direction.
Right. And because you can apply this reasoning to any particle, no matter how small, Leibniz concluded that everything must be elastic and therefore infinitely divisible, which completely contradicts the whole idea of indivisible atoms.
Right. If it's divisible, it's not an atom. So no perfectly rigid, unchanging atoms bouncing around like billiard balls.
Exactly. And another big argument he had against atomism was based on his principle of plenitude. This idea is really tied up in his theology and metaphysics. It basically says that God, being perfectly good and powerful, would create the most complete and perfect universe possible. And Leibniz thought that a void, like truly empty space, that would be kind of a flaw in God's creation. It would be like incomplete, not as full of being as it could be. And similarly, he believed that even the smallest atom, it could be even more complete and perfect if it was further divided.
So a universe packed with infinitely divisible matter is more perfect than one with indivisible atoms in empty space.
That's his argument.
It's interesting, this idea that more complexity and diversity equals more perfection. Now, I know he had this other argument based on Descartes' idea of a plenum, a universe completely filled with matter.
Yeah, this one's a bit more obscure, but it's really cool. So Descartes was talking about how circular motion in a plenum requires the particles of matter to be infinitely divided so they can adjust to the flow.
Okay.
Leibniz takes that idea and runs with it. He says that it means every part of matter must be actually infinitely divided and constantly moving, not just the parts involved in that circular motion.
So it's not just no smallest particles, it's
Oh.
everything is constantly being divided and is always in motion.
Right. And he goes even further with this. Because matter is infinitely divisible and always moving, he argues that no physical body can ever have a perfectly precise, unchanging shape. We might use idealized shapes in physics, like perfect spheres or cubes, but in reality, he says, matter is so complex that its shape is always changing.
Wow. So Leibniz's matter is this infinitely complex, ever-shifting, kind of mysterious thing.
Definitely not the neat, simple atoms of the atomists. Now, he also had a bone to pick with Descartes' own view of matter, Cartesian corpuscularianism, where matter is just extension space made concrete.
Yeah, I remember matter equals extension.
Right. Now, Leibniz agreed with Descartes that there's no void, no empty space. But he thought reducing matter to just extension was a huge oversimplification. He felt that view of matter couldn't possibly explain all the complexity and dynamism we see in the world.
Okay, so what were his specific issues with this matter is just extension idea?
Well, one of his big arguments was about the laws of motion. He basically cornered the Cartesians with this dilemma. They can either say the laws of motion come from the nature of extension itself, but then bodies would be completely passive and the laws we observe would be totally different. Or they could say God directly controls the laws of motion. But then for Leibniz, that would mean God's constantly performing miracles, which he thought was problematic.
So if matter is just passive extension, it wouldn't have any natural tendency to move or resist motion, which doesn't match what we see, right?
Right.
And if God has to constantly step in to enforce the laws, then the physical world isn't really self-governing. Okay, so what else did he disagree with Descartes on?
Another big point of contention was the qualitative variety of the world. All the colors, textures, smells, everything we experience. Descartes tried to explain all that solely through the motion and arrangement of extended matter. But Leibniz argued that if you freeze time, at any given instant there's no motion. So motion can't explain the qualities we experience at that instant. And if the world were totally homogeneous, the same, everywhere, at every instant, it would stay that way forever, even with motion. It'd like a blank film strip. Every frame is the same, so the movie is just a blank screen.
So motion can't create genuine variety if all you have is featureless extension.
Right. And then on a deeper metaphysical level, Leibniz argued that true substances have to be independent and unified. He said Cartesian bodies, being just extension, they fail on both counts. They're infinitely divisible, so not really fundamentally unified. And the kind of unity they have just from moving together isn't enough for true substantial unity. He contrasted this with his own view of minds. He called them monads.
Oh.
These were simple, indivisible, unified entities, much more like true substances.
So for Leibniz, Descartes' matter equals extension view just couldn't explain the laws of motion, the richness of our experience, or even what it means to be a real substance. Which brings us to his own view, these passive powers of bodies.
Right.
So if matter is not just atoms or just extension, what did Leibniz think it was? What characterized his passive nature?
Well, you can kind of piece together his view from his criticisms. Matter's continuous, fills all space, and is infinitely divisible. That's from his critique of atomism. And it has to be more than just passive extension. It needs some inherent activity. That's from his critique of Descartes.
Okay.
But he also specifically described four passive powers of bodies.
All right, let's hear him. What are these passive powers of Leibnizian matter?
First up, you got natural inertia. Now, unlike in his early TMA, here Leibniz says that matter actually resists being set in motion.
Okay.
It's not indifferent to motion. It takes effort to get it moving, especially if it's a big object. And he saw inertia as resistance to motion itself, not just to changes in motion like Newton.
So it's not just about changing speed or direction, but about overcoming this inherent resistance to being moved at all.
Exactly. And Leibniz thought that without a continuous force acting on it, a body in motion would naturally come to rest because of this inertia.
Interesting. Okay, so that's inertia. What's next?
Next, we got solidity, also known as impenetrability. Basically, two things can't occupy the same space at the same time.
Seems pretty basic.
Yeah, but he makes a point of distinguishing it from Descartes' idea of extension, which is just about taking up space, and from hardness, which is about resistance to changing shape. He has this cool thought experiment to objects pushed into a tube filled with liquid. The liquid resists being compressed because it can't be in two places at once, even though it's easily deformed.
Ah, so it's solid, but not necessarily hard. That makes sense.
Yep. Third, we have firmness or cohesiveness. That's a body's resistance to being broken apart or scattered. And Leibniz says this isn't due to some fundamental attractive force, like Newton's gravity. He thought that was a cop-out, just attributing it to this mysterious, unexplained force.
Okay, so how did he explain it?
He said firmness arises from the pressure of surrounding bodies pushing inward. It's like if you have a bunch of small cubes filling space. A hard object moving through that would encounter resistance not because the cubes are attracting each other, but because they're all pushing on each other, holding their shape.
Right, so it's about those local mechanical interactions, not some far-reaching force.
Exactly. And finally, we have physical extension itself. Now, this one's a bit of a head-scratcher.
Yeah.
Leibniz says bodies do occupy space, but extension isn't a fundamental property of matter. He sees it as a result of the more fundamental power of resistance solidity. So a body's extended because it can resist other bodies, not the other way around. It's like reversing Descartes.
So the space a body occupies is not primary, it's a consequence of its power to resist. That's wild. All right, so we've covered these passive powers, how matter resists change, how it takes up space, all that. But Leibniz also insisted on the crucial role of active forces. This seems like where his physics gets really unique.
Absolutely. He argued that a complete picture of the physical world has to include active forces. You can't just describe the passive stuff, how things resist change. You got to understand how things actively initiate change, too.
Okay, and this is where that famous brief demonstration comes in, right?
Yeah.
The one that challenged Descartes' conservation law.
Right. So Descartes had this idea of the conservation of quantity of motion mass times velocity, and he said this was a fundamental law based on God's unchanging nature.
Right. God's unchanging, therefore the total quantity of motion in the universe is unchanging.
Yeah. But in his brief demonstration, published in 1686, Leibniz goes after this principle. He wants to show that it's not a good measure of force.
How does he do that?
Well, his argument rests on four premises that were pretty much common sense back then. First, he says the force needed to lift something to a certain height is the same as the force it gains by falling from that height.
Okay, that makes sense.
Second, he says that a 1-pound object falling 4 meters gains the same amount of force as a 4-pound object falling 1 meter.
Right, so the force is equal even though the distances and weights are different.
Exactly. Third, he uses Galileo's law of falling bodies, which basically says the distance an object falls is proportional to the square of the time it's been falling.
Got it.
And fourth, he relies on this big principle, the equality of cause and effect.
Okay.
Meaning the total force in the cause has to equal the total force in the effect.
Right, makes sense.
So using these premises, he basically demolishes Descartes' idea. He shows, first, that quantity of motion mass times velocity isn't a good measure of force. He uses this example of falling bricks. According to his second premise, a 4-pound brick falling 1 meter and a 1-pound brick falling 4 meters have the same force, but their quantities of motion are different.
So the amount of oomph is the same, but the quantity of motion is different.
Oh,
Yeah, that's the same.
exactly. Second, he shows that vis viva mass times velocity squared is a good measure of force because it's the same in both those brick scenarios.
Okay, so vis viva seems to track the actual forcefulness better.
Yep. And third, he argues that it's vis viva, not quantity of motion, that's conserved in physical interactions. He uses a seesaw as an example. A small weight falling a large distance can lift a large weight a small distance. The vis viva stays the same, but the quantity of motion changes. And this supports his fourth premise, the equality of cause and effect.
That's a pretty elegant argument.
Mm.
He uses these simple examples to take down a core idea of Cartesian physics.
Mhm.
Now, you mentioned earlier that this equality principle had broader implications for his thinking.
Oh, yeah, for sure. In his early work, he thought the equality of cause and effect was a, absolute physical truth. But later on, he starts seeing it as a contingent truth, meaning it's true in this world, but it didn't have to be.
Okay.
He thought God, in his infinite wisdom, chose to create a world where this principle holds. And this led him to some pretty big conclusions.
Such as?
Well, he started thinking that the laws of motion and force, they're not necessarily fixed and absolute. They could have been different. And he saw the success of the conservation of vis viva as evidence that God designed the universe with a purpose, a divine plan.
So for Leibniz, understanding God's plan wasn't just for theologians. It could actually help us understand the laws of physics.
Exactly.
Now let's dig a bit deeper into these active forces. I know he talked about vis viva, living force, but also vis mortua, or dead force. What's the difference between the two?
So vis viva is all about motion. It's a measure of a body's ability to do work because it's moving, like lifting something or making something else move. And Leibniz said vis viva is conserved both in individual interactions and in the whole universe. But then there's the problem of inelastic collisions, where some of the vis viva seems to disappear.
Right, like when two clay balls collide and stick together, they lose some of their speed.
Exactly. So Leibniz explains this by saying that the vis viva isn't actually lost, it just gets transferred to the smaller parts of the bodies.
So the energy goes from large-scale motion to tiny internal vibrations and stuff.
Yeah, basically. Now, vis mortua dead force is a little trickier. It's the force a body has even when it's at rest, like the potential to move. He also called it solicitation, conatus, or impetus. And he saw vis viva as a kind of accumulation of all these tiny dead forces acting over time.
So dead force is like potential energy, and living force is kinetic energy.
That's a good way to think about it. And vis mortua was also connected to the study of statics, forces on objects that are not moving.
Okay. Now, how did Leibniz's ideas about force compare to Newton's? I know he was pretty critical of Newton's idea of gravity as this mysterious force acting at a distance.
Yeah, Leibniz wasn't a fan of that. He thought Newton was basically giving up on explaining gravity in a mechanical way, through contact and interaction. He saw it as a step back towards those old occult qualities that the scholastics used to talk about. Leibniz was all about explaining things in a way that made sense, no mysterious action at a distance allowed.
So he wanted forces to be grounded in the actual physical interaction of bodies, not just this spooky action across empty space. Now, this leads to his idea of primitive and derivative forces.
Right.
What are those, and how do they relate to the forces we actually observe and study?
So in his Specimen Dynamicum, Leibniz makes this distinction between these two types of forces. Derivative forces are the ones we deal with in physics, like forces in collisions, gravity, all those observable interactions. But he says these are just the tip of the iceberg. They're actually modifications or expressions of deeper, more fundamental forces that he calls primitive forces.
So the forces we see are just the outward manifestations of something more basic, more metaphysical.
Exactly. And most scholars think that Leibniz believed these primitive forces were the ultimate source of all the forces we observe. Active primitive forces give rise to active derivative forces, and passive primitive forces give rise to passive derivative forces. And he even compares primitive active force to the Aristotelian idea of the soul, the source of activity and organization in a thing. And he compares primitive passive force to the Aristotelian idea of primary matter, the raw stuff that receives form.
So he's bringing back these ancient philosophical ideas to explain his modern physics.
In a way, yeah. Now, things get even more interesting when we consider his panorganicism, the idea that everything is made up of these tiny living organisms all the way down.
Okay, the bugs all the way down thing,
Oh.
right? How does that fit into all this?
It's complicated. Some scholars think that in his middle period, Leibniz had this view that organisms, unities of form and matter, were the most fundamental things. So all the forces we see would ultimately come from the interactions of these tiny organisms.
So even a rock would be made up of these countless little living things.
That's the idea.
That's kind of trippy.
Yeah. But later on, he shifts towards this monistic view where everything is ultimately made of monads, these simple mind-like substances. And in this later view, even those organisms are seen as just phenomena appearances grounded in the activity of monads. And forces, too, have this kind of chain of dependence. The forces of big things come from the forces of the smaller things they're made of, all the way down to the forces of the monads.
So it's like a nested hierarchy of forces, all originating from these fundamental mind-like monads. Okay, that's a pretty wild picture. Now let's get to his ideas about the laws of motion. I know he had some serious disagreements with Descartes on this front, too.
Yeah, he did. And it wasn't just about the conservation of motion. He had some fundamental issues with Descartes' whole system of laws.
Like what?
Well, as we've talked about, he thought Descartes' laws violated the conservation of vis viva, which for Leibniz was a deal breaker. But he also had a problem with the way Descartes' laws handled collisions. He thought they led to these sudden, discontinuous changes, which went against his principle of continuity.
Right, that smooth change principle.
Exactly. He had this example with two balls, B and C. If ball B is just slightly bigger than ball C and they collide, ball C bounces back while ball B keeps going. But if they're exactly the same size, they both bounce back. Leibniz said this tiny difference in size shouldn't cause such a drastic difference in the outcome.
Right, it seems like the results should change more smoothly. And you said earlier that he saw this principle of continuity as being connected to God's design of the universe.
Yeah, he did. He thought a world with discontinuous laws would be less harmonious, less perfect. And this idea reinforced his belief that the laws of motion are contingent. They could have been different. And he saw the elegance and smoothness of the laws we do have as evidence for God's wisdom and benevolence.
So for Leibniz, even the predictability of physics was a sign of God's goodness. Now, what was his own system of conservation principles that he proposed as an alternative to Descartes?
So when it comes to describing motion, Leibniz's laws were actually pretty similar to the ones developed by Huygens and Wren, those empirically successful laws that were gaining traction at the time.
Yeah.
But instead of trying to derive those laws from deep metaphysical principles, Leibniz went a different route. He based his system on three fundamental conservation laws.
All right, let's hear him. What were these three conservation laws?
The first one was the conservation of relative velocity. Basically, in a perfectly elastic collision, where no energy is lost, the speed at which two objects approach each other is the same as the speed at which they move apart after colliding.
Oh, okay.
And Leibniz thought this was tied to the idea that their ability to affect each other through motion is conserved.
Like the energy of their interaction is preserved.
Yeah, something like that. The second law was the conservation of quantity of progress. It's kind of like the modern idea of conservation of momentum. The total momentum of a system stays constant.
Right.
But Leibniz was careful to use sign velocities, meaning the direction of motion matters. So it's not just the amount of motion that's conserved, but the total motion in a specific direction.
Okay, so it takes direction into account.
Exactly. And the third one, of course, is the conservation of vis viva, that mass times velocity squared thing. It's conserved in perfectly elastic collisions. And in inelastic collisions, where some vis viva seems to disappear, Leibniz said it's actually just being transferred to the tiny parts of the objects.
Right, like we talked about before. Now, he showed that you could derive any one of these laws from the other two. Did he see them all as equally fundamental? Or did he prioritize one over the others?
He definitely considered vis viva to be the most fundamental one, probably because it played such a central role in his brief demonstration against Descartes.
Oh, yeah?
And also, he really believed that vis viva was the best way to capture a body's true power or capacity to do work.
Yeah, it makes sense given his focus on active forces and the importance of vis viva. All right, let's move on to his ideas about absolute versus relative motion and that big debate he had with Samuel Clarke about space and time. This feels like where a lot of his ideas come together.
Definitely. Leibniz's whole view of reality, with its focus on active forces and his rejection,